Alright everyone, welcome back. Today we're going to be talking about infinite limits. We're going to be continuing our conversation with limits. We'll be talking about limits for this lesson and the next one as well. So recall, last time we defined what a limit is, and we spoke also about how to evaluate limits of linear functions, polynomial functions, rational functions, exponential functions, and trigonometric functions. Alright, so today we're going to be continuing the conversation on limits. And we're going to talk about two special limit scenarios that may appear. So today we will focus on one of two limit scenarios that may appear when evaluating some functions, some limits of functions. So this is something that's going to happen throughout the course, where you're going to have you may take a limit, and the limit may be what we call infinite, or the limit may be at infinity. So I'm just going to quickly talk a little bit about these two scenarios. Today we're going to be talking about just infinite limits. Next time we'll be talking about limits at infinity. So an infinite limit happens when function values increase or decrease without bound near a point. Whereas a limit at infinity happens when the independent variable x increases or decreases without bound. Okay. So these are the two limit scenarios that we're going to be talking about in the next couple of lessons. It is very important to understand both of them and the differences between them as well, because they will again come up a lot. So let's talk about a motivational example. So let's consider the function f of x equals 1 over x squared. We will see what happens to the function as x goes to 0, and also what happens as x goes to plus or minus infinity. All right, so let's first of all graph this. So I'm going to actually really quickly just graph this in GeoGebra so you can see how it looks. Kind of looks nicer in GeoGebra. So f of x of x equals 1 over x squared. So as we can see, as the function begins to get closer and closer to 0 from the right on the x-axis and from the left on the x-axis, the y values, the output values, begin to get bigger and bigger. They begin to increase, and they begin to increase faster after you get below -1 from the left and below 1 from the right. At -1 you're at 1, at 1 you're at 1, and then as you begin to get closer and closer to 0, the function values begin growing very quickly. I mean, if you look at this value right here, you'll have to go all the way past what I'm displaying on the screen to actually see what the output is. So if we continue to see, the closer and closer we're getting to the y-axis, which will mean the closer and closer we're getting to 0 on the x, the higher the outputs are becoming. To the point that eventually we'll have to actually zoom in just to see, just to be able to distinguish between the y-axis and the actual function. I mean, you can see it. So that's what's going on here. So let's very quickly just illustrate this. So we have the x-axis, y-axis, and you have, much like we had over there, we have y equals 1 over x squared, which looks like this. And as we get closer and closer to 0 on the x-axis, the function values are becoming larger and larger and larger, and they're going up without bound. So as you can see, this is happening from both sides. And where what's going to happen is that although the limit here actually does not exist because we're growing without bound, we are not actually approaching a number. Remember that the way that we define limits a while back is that the limit exists if we approach a number that we call L. And here we are not approaching any number because you're just increasing without bound. Right? No matter how closer you get to 0 on the left or right, we're going to get higher and higher numbers. So the limit actually does not exist. However, we will use the limit notation to make sense of what's going on here. So although the limit as x goes to 0 of f of x equals 1 over x squared does not exist, we will use the limit notation to that's what I'm looking for, to explain this phenomenon. So here's what we will say whenever this happens. Whenever we have a situation like this, we will write the limit as x goes to 0 of something like the f of x we have is actually equal to infinity. Here the infinity symbol, so let me write this down. Here the infinity symbol indicates that f of x grows arbitrarily large as x approaches 0. And this is an example of an infinite limit. So in general, an infinite limit means that the dependent variable, remember the dependent variable is the output, often we just call it y. becomes very large as the independent variable, which we typically call x, approaches a finite number. For our example, with 1 over x squared, x was approaching 0, a series of finite numbers, an actual number, but the y values are increasing arbitrarily, and they're becoming very big very quickly. So here we say that we have an infinite limit. Now with limits at infinity, we have a whole different situation, and we will talk a little bit more about it in the next section, but I'll just mention it right now. So with infinite limits, the dependent variable approaches a finite number as the independent variable becomes arbitrarily large. So using the same example of f of x equals one over x squared, we can see that if we instead looked at the limit, if we instead focus on the limit, let's say limit as x goes to infinity of 1 over x squared, what we will have here is that that limit is going to be equal to 0. And we can see that clearly. We can see it here. So limit as x goes to infinity means that the x values are moving away from 0. They're getting very large very quickly. And as the x values are getting very big, the outputs are getting smaller. So we can see they're going down, all the way down. And this, this green line, as we saw in GeoGebra, is going to continue to go down, but it's actually never going to touch the x-axis, and it's never going to cross the x-axis either. I'll explain that, why that's the case in a few. The same thing is true when we look at the limit as x goes to minus infinity of 1 over x squared. This limit is also going to be equal to 0. So as we get smaller, smaller, and smaller, on the x-axis, the independent variable is also getting smaller, and it's approaching an actual number. And notice here, I just gave it away, the limit from the left, so the limit as x approaches negative infinity of f of x is equal to the limit as x approaches infinity from the right of f of x, which equals 0. So that means that the limit actually exists, and it is 0. So whereas limits, infinite limits, those limits do not exist, limits at infinity do exist, and you can get an actual numerical answer. So let me define informally, at least. Later on I'll be defining this very formally, but let's at least define informally infinite limits. Okay, so suppose f is defined for all x near a if f of x grows arbitrarily large for all x values sufficiently close but not necessarily equal to a, then we write the following. Let me move this down so it's not in the way of the other things. So we write the following. We write that the limit as x goes to a of f of x equals infinity. So if f is defined for all x near a, and f of x grows arbitrarily large for all x values that are very close to a, then we write that that limit is infinite. So we say the limit of f of x as x approaches a is infinite. Okay. Now, if f of x is negative, and grows arbitrarily large for all x sufficiently close to, but again not equal to a, but not equal to a, then we write the following. We write that the limit as x approaches a of f of x is minus infinity. So we say as I just said, the limit of f of x as x approaches a is negative infinity. Now, in both of these cases, the limit does not exist. Remember, infinity is not a number, it's an idea. So this does not saying that the limit is plus infinity or minus infinity does not actually meet our definition of a limit that we have from before. Before we said that the limit must be a number, must be a finite number. Okay, so let's look at a couple of limits. Let's look at a couple of examples. So example, much like before, we're going to begin with analyzing the limit graphically, and then we'll move into analyzing the limit algebraically. Okay, so let's see. We're going to analyze the given limit using the graph of the function. And the limits given is the following. Limit as x goes to 1 of x divided by x squared minus 1 squared, and the limit as x goes to minus 1 of x over x squared minus 1 squared. Okay, so if we were to graph this, let's see if we could get a graph going for this. So we have x over x squared minus 1 squared. So if we were to graph this, is how it will look. Just move down. Kind of went too far up in the previous graph. Okay, so this is how it looks. And if you don't remember how to graph this from pre-calculus, you could always make a table. So maybe I'll show you how to do that. It'll remind you. I know we did a review, but just in case, because I'm not expecting you to use GeoGebra for homework or exams. In fact, I expect you to do this by hand. But just for the sake of argument and to look at it prettier, I'm doing it on GeoGebra. So we have to analyze this using the graph, the limit as x goes to 1 and the limit as x goes to minus 1. Now, if you notice, if we focus just first on the limit as x goes to 1, if we go from the right side, as the x values get closer and closer to 1, the y values begin going up to plus infinity. If we go from the left side, as the x values become smaller and begin to get closer to 1, the y values are also very quickly going to infinity the closer we move to 1. So we can clearly say that the limit does not exist and that the limit is going to be infinity. Similarly, if you look at the minus 1, if you notice as the x values from the right get closer and closer to minus 1, the y values on the graph begin to get closer and closer to minus infinity. They begin to get very big in the negative direction. And similarly from the left side, they closer and closer to get to minus 1 from the left side, the output values of the function also begin to grow on the negative side very quickly. So that's going to minus infinity. So we can clearly see that for both cases, the limit does not exist, but we can say that the limit is infinity for the first one and the limit is minus infinity for the second one. So, as we can see from the graph, let me sketch it first. So like I was saying, if you don't remember how to graph these things, you always make a table. A table will always work. So that will be x squared minus 1 squared. I always put y on the left side, on the right side. And then sometimes I put the point. So I'm only going to pick, 3 points, and or maybe more. Let's see, I'm going to pick, let's do 2, 0, minus 2. I think those 2 will be fine. Those 3 will be fine. So let's see, 2, but it's still on the top. So 2 squared is 4, minus 1 squared. So that's going to be equal to 2 over 4 minus 1 is 3, square is 9, so 2 over 9. When you have a 0 in the numerator and the denominator is not 0, so that's going to be negative 1 squared, then this whole thing is going to be actually 0. And minus 2 squared, minus 1, all that squared. So it's just going to be minus 2 on the top. And then the bottom should really be the same as the first one, so it should be minus 2 nines. Because we're gonna have a plus 4 minus 1, which is gonna be 3, and 3 squared is gonna be 9. And here you could have an idea of what we're doing. I'm really skipping on something because I'm gonna introduce it in a second, but this from pre-calculus you should know, and if not, you should watch the review of pre-calculus, and that's what's happening at negative 1 and 1. If you remember, this will be called our vertical asymptotes because they make the denominator of the function equal to 0. When that happens on a rational function, we have vertical asymptotes. So we have minus 1, 1. So we have this imaginary dashed lines where the function does not cross. And now we have that to the right side of 1, we're always positive. And I'm kind of, not mentioning that the horizontal asymptote here is 0. I'm just skimming over that. I hope that you remember what that is as well. If you don't, again, go over the review video. So that's always going to be positive, so it's going to be up there. To the left side of minus 1, we have minus 2. This is negative, so that's always going to be negative here. So it's going to be going down. And then you just have to worry about what's going to be going on in the middle section here. We have that this middle section is going to be 0 here. If you wanted to, you could find a point to the left and right side like minus 1/2 and 1/2. And you will see that one of them is going to be positive. The other one's going to be negative. So this looks like the cubic function on the inside. And when you're in between vertical asymptotes, you are allowed to cross the horizontal asymptote. So if you don't remember that, well, now you do. So here's how we'll graph something like this. So on an exam, I don't want you to use GeoGebra, and I'd rather you do this by hand, because in the future, if you take a class in person, and you obviously will not be allowed use of a graphing calculator, at least not at Lehman. So you will have to know how to do this by hand. So if you move on to Calculus 2, Calculus 3, you're expected to know how to graph these things by hand. Okay, so that's how you will graph them. So going back to what we were talking about, we can see that this particular graph, so let me type this out. We can see from this graph that as x approaches 1, from the left and the right side, the values of f grow arbitrarily large. Notice, put an R after this. There's no R there. Therefore, by what I define above about infinite limits, the limit does not exist, and we write limit as x goes to 1 of x over x squared minus 1 square equals infinity. That's for this first one. As we go to 1 from the left and the right side, we see that we are going up to infinity on both sides. Okay, so how about the second one? For the second one, as x approaches -1, again from the graph, so as x approaches -1, we see that the values of f are negative. That we can see from the picture, they are all going down, and they grow in the negative direction. Very large and very quickly. So we have that the limit as x goes to -1 of x over x squared minus 1 squared is equal to minus infinity. Again, these are two-sided limits, and the limits are infinite. One of them is positive infinity, the other one is negative infinity. Now, notice that, again, these are two-sided limits. Notice that these are two-sided limit computations. Also notice that both limits, even though they went to infinity, and I'm saying that they do not exist, they both are, we're saying, are equal. The left and right side limits are plus infinity for the first one, for this one, and minus infinity for this one. So, you know, there is some I guess I'll call it an analog to what we were doing before in last class, when we define whether a limit exists or not, the two-sided limit exists or not. If the limit was going in, we're going in opposite directions as they go to 1 or -1, for example, then you clearly will say the limit does not exist. You will not say that the limit is infinity or the limit is minus infinity. Like, for example, if you had something like this, let's say you have 1, and here's your vertical asymptote, and you had one function going like one side going like this and the other one going like this, then as x goes to 1, the limit of this function, let's call it g of x, does not exist. because we're going in opposite directions. So we cannot even say that the two-sided limit here is going to exist. So that's one thing that we're going to be building up to. Now let's talk a little bit about one-sided limits, because although the two-sided limits does not exist here, the one-sided limits does exist. You could take the limit from the right and get plus infinity on this side, and you could take the limit from the left and you get minus infinity on that side. So that certainly can happen, and clearly you can see it there. So another definition is for one-sided infinite limits. Well, suppose f is defined for all x near a with x being greater than a. If f of x becomes arbitrarily large for all x's sufficiently close to a with, again, x bigger than a, then we write the following. We write that the limit as x goes to a from the right side of f of x is equal to infinity. Now, I'm only going to write this for the right side, but this is analogous to the other limits from the left side, and so on as you move away from a or closer to a. So the definition for this does not change very much when you do it for, let's say, limit as x goes to a from the left side. In this case, you're gonna do x is less than a, so that you'll change the x less than a, and then you'll have minus infinity for one of them, and then plus infinity for another one. So, if you have something like this, then you may have plus infinity, you may have minus infinity. So you may also have limit as x goes to a from the right side of x. You could have that also be minus infinity. And again, limit as x goes to a from the right side, from the left side, can also be minus infinity. So this is analogous to what we had prior in the previous lesson. So all you have to do is play around with this x bigger than a and x less than a. So just to illustrate it a little bit, let's say we have a here. That's our vertical asymptote. Then we could have our function look like this. And as we get closer and closer to a, the y values are going up to infinity. So that's one scenario. Here, clearly, limit as x goes to a from the right side, f of x is infinite. This other scenario will be, again, we have a with a vertical asymptote, and now we have something like this, where as you go to a from the right side once more, in this case, the function values are becoming negative. So we have that this limit is minus infinity. So we will have limit as x goes to a from the right side be minus infinity. And similarly, once again, you could have the following case where the x values are approaching a from the left side, and the function values are increasing to infinity as this happens. So here the limit as x goes to a from the left side is going to be plus infinity. And finally, as you probably by now would have guessed, we may have this scenario where as the x values are approaching a from the left side, the function values are going to minus infinity. So here, the limit as x goes to a from the left side of f of x is minus infinity. So these are the four scenarios for one-sided limits. And again, they will play a big role as we move along in the semester. We will see this come up again when we are taking limits of other type of functions. Sometimes we may take a limit of a piecewise function, for example. So it's important that you understand these things. Now, this is something that I mentioned during the review, but just so you know, in all of these examples, the line x equals a, which is that dashed line, the vertical line, is called the vertical asymptote. The vertical asymptote is a vertical line that is approached by the graph of f as x approaches a. So this, again, we saw during the review. So I'm just going to define it once more. And let me do it with a pen. Just bear with me. So if the limit as x goes to a, f of x equals plus or minus infinity, or the limit from the right as x goes to a, f of x is plus or minus infinity, or the limit from the left as x goes to a of f of x is plus or minus infinity, then the line, this is a formal definition of vertical asymptote, the line x equals a is called the vertical asymptote. So if you're riding the train on your way home from class and somebody stops you and they give you the graph of a function, they claim that, some line, let's say x equals 5 is a vertical asymptote, then you could prove them right or wrong by simply taking the limit as x goes to a of that particular graph. And if you get plus or minus infinity from the two-sided limit or any of the one-sided limits, then you have a vertical asymptote. So this is something very useful when you're riding the train and you get stopped by random people asking you to find whether you have vertical asymptotes or not. Happens very often in New York City. All right, so let's do another example finding vertical asymptotes graphically. So, example, let us examine the following function g. Describing its vertical asymptotes and finding the limit as x goes to 1, x goes to 3 from the left, and x goes to 3. So when I don't say left or right, that means the two-sided limit. So as x goes to 1, this means two-sided. As x goes to 3, that means two-sided. So if I do specify, then when I specify it, I do mean the one-sided. All right, so let me give you the function g. So g is the following function. g of x equals x minus 2 divided by x minus 1 squared times x minus 3. Let me rewrite this. So x minus 2 over x minus 1 squared times x minus 3. All right, so first of all, what are the vertical asymptotes? So what are the vertical asymptotes? Well, recall that the vertical asymptotes happen when the denominator is equal to 0. So, well, also recall the following. There's a well-known rule. If you have a times b equal to 0, then either a equals 0 or b equals 0. So here we have x minus 1 times x minus 3. And we really have two x minus 1s here being multiplied because it's being squared, and 1x minus 3. So I really just have to worry about when x minus 1 equals 0 or x minus 3 equals 0. So x minus 1 equals 0 if x equals 1, and x minus 3 equals 0 if x equals 3. If you plug in 1, you get 0. If you plug in 3, you get 0. So these are the vertical asymptotes. So x equals 1 and 3 are vertical asymptotes. So that's number 1. So now, what happens if I take the limit as x goes to 1 of g? Well, let's see. If we were to graph this, function, here's what we'll have. So we could make a table really quickly. We have x minus 2, x minus 1 squared, x minus 3, and y. So we already have the vertical asymptote, so I have one at x equals 1 and x equals 3. Maybe I shouldn't have done this line over here. So we have 1 and then we have 3, which is my x, my y. So I'm going to figure out what we are looking for when we have 0, at 2, and at 4. Typically, I always look for value to the left of the asymptote, to the right of the asymptote, and in between. So if we plug in 0, we have minus 2 in the top. In the bottom, we have negative 1 squared. That's just going to be 1. And minus 3, so it's going to be a positive number because we have minus 2 over minus 3, so this is 2/3. Yeah. So that means that to the left side of the asymptote of this line, we are always positive. For 2, if we plug in 2, we have 0 in the numerator, and then in the denominator, we just have to worry about getting 0, so we have 2 minus 1 is 1, and obviously squared, and 2 minus 3 is minus 1, but the numerator is 0, so this whole thing is going to be 0. So it means we have a point here. And finally, we have the 4, so we have 4 minus 2 is 2 in the top, 4 minus 1 is 3, and 4 minus 3 is 1, so it's always positive as well. So I don't even care what it is for the most part. As long as it's positive, I already know where it's going to be. Because I'm just doing a sketch. I mean, if I was actually plotting this, then I will care about what the numbers are. This is going to be 9. So this is going to be positive on this side as well. And then in the middle, we're going to have the same situation as before, but we just have to be careful. So you could pick 1.5 and 2.5 if you wanted to. But this is going to look like the reflection of the cubic. It's kind of going to look like this. So that is the graph of this function. So now we could easily see what the limit is going to be as x goes to 1, the two-sided limit. And the reason why we could easily see it is because now we could visualize it. If we go from the left side towards 1, we can see that the y values are getting very big. If we go from the right side to 1, we could also see that the y values are getting very big. So this limit does not exist, but we can say that the limit is infinite, plus infinity. That's from the picture. You could see that it's going to infinity on both sides. So that limit is infinity. Now, for x goes to to 3 from the left side, this one we have to be a little bit more careful. 3 is here, so as we go towards, I'm going to try to use a different color. Or crash my computer. One or the other. Alright, so let's get back to where we were. Right, so if we approach this value, let me use this color, from the left side, we can see that as the x values get closer and closer to 3 on the left, the y values are going down to negative infinity. So as the limit of x goes to 3 from the left side of g of x, we go to minus infinity because our values just keep going down. Finally, the limit, as you can see, the limit, as we could see, of g going to 3, x going to 3, the limit as x goes to 3 from both sides of g of x, it's actually not going to exist. And we could see that from the picture. You know, if you really wanted to see it, you'll have to find the limit from the right side of g of x. The limit from the right side of g of x is plus infinity because the values are going up as we get closer to 3. So it's plus infinity. But again, because the limit from the left and the limit from the right are not equal, then the limit simply does not exist. So we say that the limit just doesn't exist when this is the case. Okay, so now this is what happens when we want to compute the limit graphically. If you wanted to compute a limit graphically, especially a limit at infinity, we simply plot it and then we figure out what's going on from the left and the right side. Now, many infinite limits are analyzed by simple arithmetic. So let's analyze limits analytically. So like I was saying, many infinite limits are analyzed using a simple arithmetic property. And that is the following fraction, a over b. This fraction goes very large if b goes to 0 while a remains non-zero. So this particular fraction grows arbitrarily large as b goes to 0 and a remains non-zero. So as b begins to get smaller and smaller and smaller, and a stays constant, then the actual limit will go towards infinity or minus infinity, depending on what you're working with. So for example, let me just give you an example. So for example, take for example the fraction 5 plus x over x. Limit as x goes to 0 from the right. So if we were to evaluate this particular limit, we could begin by making a table, let's say, of values for x, and then figuring out what the output is. And we could start with, let's say, 1. We're getting closer to 0, so I could begin with 1. So if we begin 1, we have 5 plus 1 over 1, so that's just 6. And then you could cut that in half, so you could do 0.5, let's say. So you'll have 5 plus 0.5 divided by 0.5, and if it's okay with you, I'm going to write the 0.5 as a fraction in the denominator. I mean, I could do it in the numerator too. So we'll have 5.5 divided by 1/2. Now, what is this the same as? Well, instead of dividing by 1/2, I could multiply by 2 over 1. So if I rewrote the 5.5, if I had written that as a fraction, you will see that this is a complex fraction. So we could just multiply instead of divide. So that will be, I believe, 11 if we were to do this. And then you could continue to do this and move the x values closer and closer to 0. So now if you do 0.01, let's say, you have 5 plus 0.01 divided by 0.01. This is the same thing as 5.01 over 0.01. If you remember, 0.01 is the same thing as 1 over 100. So this is really 5.01 divided by 1 over 100. And again, by the same technique of keep, change, flip, we're going to really multiply 5.01 by 100 over 1. So that's going to be 501. So notice that the closer I'm getting, and if I could continue this, the closer I get to 0, the bigger I'm making the actual value or the outputs. Because now this is going to be 5.001 divided by 1 over 1,000. So now it's going to be 5,001 when you compute it. So I went from 6 to 11 to 501 to 5,001. And as I keep making the x values very small, meaning I'm getting them closer and closer to 0, I'm making the output values very big. I'm already at 5,001. So, if we continue, you'll even get to like 500,000 and so on, because they're going to get very big. So that is how you analyze limits analytically. You could rely on that particular fraction, the fact that as the x values get very small, the y values get very large. And again, this is because the numerator is non-zero and the denominator is getting closer to 0. So let's do another example. We're going to have the limit as x goes to 3 from the right side of 2 minus 5x over x minus 3. So here we see that the numerator, if we were to just plug in 3, notice that if we plug in 3, the denominator is going to be undefined. But that's okay. We don't have to plug in 3 on the denominator right away. We could, however, see that if we were to plug it in the numerator, we will have 2 minus 5 times 3 over, let's say, x minus 3. I'm not really plugging it in. Just trying to see what's going to happen in the numerator. And we could see that 3 times 5 is minus 15, so this is going to be 2 minus 15 over x minus 3. So it's going to be minus 13 in the numerator. And we just have to worry about what happens in the denominator as x gets closer and closer to 3 from the right side. So let's say x is approaching to 3 on the right side. Well, we know that if x equals 3, we're going to get 0 here. So what if I had, I don't know, something like 2.999? So if I had 2.999 there, we know that the numerator it's going to limit at 13. So it's going to be pretty much fixed at that value. All right, it's going to approach that value the closer and closer we get to 3 from the right side. But if we're looking at the 3, then we will have, let's say, 3 point, so I'm going from the right side, 3.0001, right? Minus 3, and we're going to be in the same boat. So I'm going to have like minus 13, something like minus 13 divided by 0.0001. And it's going to be the same as this situation, where this is really the same as minus 13 over 1 over 1,000. Actually, 10,000. And this is going to be negative 13,000. So we could see that the smaller you're making the 3, the closer you're getting to 3 from the right side, the bigger you're going to be making this output value. So, and notice that because the numerator is negative, that means that the whole fraction is going to be negative. So this is actually going to be tending to minus infinity. So that is something to keep in the back of your head. This numerator is always going to be negative, no matter what value of x you put in, because we're making x go closer and closer to 3. So, you know, if you were to put in 3 like we saw, we're always going to get negative 13. So we could say that the limit as 2 minus 5x over x minus 3 goes to 3 from the right side is always going to be equal to negative infinity. Let's do another one. How about limit as x goes to 3, this time from the left side, of the same function, 2 minus 5x over x minus 3. And again, we could have plotted this and we could see what happens, but this is just to show you that you don't need to plot everything that you come across to actually solve it. So similarly, like before, we can see that on the top, if we were to just plug in 3, again, we will still get minus 13. So in the numerator, that's going to be equal to minus 13. But in the denominator, we have a little bit of a different situation. Here we're plotting positive numbers because we're to the right of 3. Here we'll be plotting, for the most part, negative numbers because we are to the left of 3. And we're getting closer and closer to that 3. And because these values now are going to be below 3, then this denominator is also going to be negative. So the closer and closer we get to negative 3, you will see that we will always be left with a negative value in the denominator as well, because we will have something, for example, like this. Let's say we put now 2.999 minus 3. So now instead of plotting in 3, I'm plotting in 2.999. We know again that the top is going to be bounded to minus 13. So this is going to be something very close to minus 13 when you do it. It may be like 12.99 in the top. So let's just assume that it is. I haven't done this calculation. So let's assume that it's minus 12.99. Because we know that this is eventually going to limit to negative 13. In the denominator, this is going to be equal to what? It's going to be equal to negative 0. And then here, where are we going to have? Well, we're going to have the following values. We're going to have, what happened to my pen? One sec.